So good afternoon, everyone. Welcome to this edition of the NITheCS Colloquium. My name is Francesco Petruccione, and our speaker is Professor Sam Cohen from the University of Oxford and the Alan Turing Institute. Yeah? I will invite now Dr. Mesias Alfeos, who knows the speaker very well, to briefly introduce him to you. Mesias.
Yeah. Thank you very much, Prof. Francesco, for the opportunity to introduce our speakers for today. Colleagues, and good afternoon, everyone, the one online as well as the one in the room. It gives me a great pleasure to welcome Professor Sam Cohen to our seminar or colloquium for NITheCS. Professor Sam Cohen is an associate professor at Mathematical Institute at Oxford University, and he is also a theme lead for machine learning in finance at the Alan Turing Institute. He is an associate member for Oxford Mann Institute and a member of Oxford Near Finance Big Data Lab, and also a senior research fellow at New College in Oxford. His main research interests are in stochastic analysis and mathematical finance. In particular, he's interested in interaction between statistical and machine learning, decision-making, as well as control and uncertain aviation. Today, he will talk to us about approximating PDEs with wide neural networks. And guys, colleagues, help me to welcome Professor Sam Cohen to this, and looking forward to your talk. And Sam, please, with great pleasure to have you here today. Thank you.
Well, thank you. It's a great pleasure to be here, and I understand your seminars are normally on Monday, so thank you for adjusting for my timetable. It is great to be here. I'm going to talk about some work that I've been doing with my colleague Justin Serignano and our student Deching Jiang, working on some problems less to do with finance, or they're related to financial problems. Lots of things in finance involve PDEs, but we're going to not focus on the finance. We're going to focus just on the interaction of machine learning and numerical methods for today. It's lovely to be here in person, so I would say if you do have questions, please interrupt me as I go. It's far more fun if we do it that way. Giving talks online was always like screaming into the void, so it's nice to be able to see another face. Okay, so what we're going to try and do is we're going to look at trying to solve numerically PDEs using some of the tools of machine learning. So in particular, finding numerical solutions to partial differential equations is a big problem, a very common problem. In my world, so in mathematical finance, it comes up in pricing, it comes up when you try and understand hedging and risk management. It also comes up when you do optimal control, and more generally in engineering problems, you get PDEs that you need to solve. It comes up in mechanical problems. You're looking at solving for fluid flows over various domains. It comes up in economic systems, in physics. We solve many PDEs in physical systems. And so generally, this is an interesting thing to do. And the problem with PDEs is that apart from a few special cases, we do not have closed form solutions. Unlike ODEs, where we have a lot of good methods for providing closed form solutions, for PDEs, there's very few. So what we're going to talk about, and I'll sort of give the assumptions as we go along. I'm trying to find a function U, which is a map from Rn to R, so from n-dimensional space to one-dimensional space, which satisfies GU equals 0, where G is some differential operator, something that involves taking derivatives. It could be that this does something nonlinear with the derivatives. Mainly, we're going to be interested in linear cases today, as we'll see, but in principle, this could be nonlinear. And together, there's some boundary conditions. So on some bounded space, I have behavior of U on the boundary. Now, traditional methods for solving this, they suffer from what's called the curse of dimensionality. which is a term coined by Bellman in the 60s, really, which is that the cost of solving these equations grows exponentially in n. And you can think about it in a very easy way. If I want to approximate a derivative in one dimension, I just take 2 points. So 2 points gives me a way of calculating the change between 2 points and hence the derivative. And if I'm in n dimensions, to do a similar simple algorithm, which gives me all the derivatives separately, I need 2 to the power of n points. So when n gets large, this becomes computationally very, very expensive to evaluate. And this has led to interest in using machine learning techniques, which have a nice property that they often work very well in high dimension. I see someone's raised a hand. Francesco, I guess you're in charge. What are we going to do? Okay. Okay, I'll just ignore it. That's fine. All right. So I'm not going to use all machine learning techniques. Machine learning is really just a very big area which has many different parts to it, of a mixture of data engineering, of statistics, of numerical methods, optimization. We're going to talk about one of the more common things, which are artificial neural networks. So what are neural networks? Well, these are ways of approximating functions out of very simple pieces. In particular, they use composition of simple functions. So you take linear projections and then you apply a nonlinearity component-wise to your linear projection. So you take linear functions, component-wise, you apply a nonlinearity, then you combine them linearly, and this is your function approximator. Now, there's a classic result by Sibenko in 89, and then the version we're going to be using quite a lot is Hornick in 91, which says, if I take a very, very wide neural network, so I take my input, I do lots of different linear things to it, possibly infinitely many, but a very, very large number, apply almost any nonlinearity to the result, and then combine them linearly again, then I get something which can approximate any function very well. In particular, so if my activation function, the nonlinearity I apply, has k derivatives, so it's continuous ck, then the neural networks are dense in the HK Sobolev space. What does this mean? Well, it's just the space of functions which have k derivatives in a weak sense, and those derivatives all live in L2. So we know that we can approximate any function and k of its derivatives arbitrarily well using some neural network. Now, I don't know how to find it, don't know what it looks like, but I know it exists. There is some approximating sequence of neural networks that approximate any function. So why do we think these work well in high dimensions? Well, one of the more hand-waving ideas about neural networks is they're good at learning moderate dimensional representations of high dimensional objects. This is why they're very good at, say, processing pictures. A picture is something that lives in a very high dimensional space. There's lots of different pixels. They vary in all sorts of different ways. But if I look at a sequence of photographs, the vast majority of photographs are, if you like, relatively similar. They have similar structures, similar relationships between the pixels, and that means that they live in some low dimensional space embedded in a very high dimensional space. So there might be 3 million dimensions of pixels, but there might be only 100 dimensions of interesting images. And neural nets are good at finding that 100 dimensions and using them. And so this gives us a way of potentially of avoiding the curse of dimensionality. Okay, so we're going to be interested in solving PDEs, so let's think about how we would go about doing this. Okay, so we're interested, let's add a few assumptions, let's make things a bit more definite. We're interested in solving a PDE with a Dirichlet boundary condition. So I have my function u that I'm interested in. I apply some operator g, which takes some derivatives and adds them together, does some things to them. And I need this equals 0 on omega, and u equals f on the boundary of omega. Well, what's omega? It's some domain in real space, and we'll assume that it's bounded, subset of Rn, and it has a nice, through little bit more than 3 times differentiable boundary. So its boundary is regular enough to make sense. I'm going to assume that I have some measure, mu, on omega. And you can think of this as just the uniform Lebesgue measure. I'm able to sample from my space omega, but I'm going to leave it a little bit more flexible by saying it's just a measure and it has a continuous non-negative density with respect to the Lebesgue measure. So it's got a density over my space where my samples are going to live. And everything I say is going to come from my measure mu. And it's convenient to leave that as a moving part of my algorithm. So what's G? Well, I've said it's a differential operator. Let's say it's second order, so it can compute up to a second derivative. It's possibly not linear. It's a differential operator. It's Lipschitz. In particular, it's a map from H2, the functions with two derivatives, to L2, the functions that are just twice integrable. So it takes something which has some derivatives and gives me a function back, and that function is not too weird. And if I give it the function 0, the result is also still integrable. And I'm going to assume that f, this boundary value, I can somehow extend it to some sufficiently smooth function on all of omega. It's defined only on the boundary, but let's just assume I can fill in my space and give you some function which has the value f on the boundary. So how am I going to go about approximating? Well, if you've studied PDEs, you know that the boundary sort of tells you a lot about the problem. So approximating the boundary correctly is very important, but I'm a very lazy man, and I don't want to approximate any more than I have to. So I'm not going to approximate the boundary at all. I'm going to somehow bake the boundary condition into my approximation. And that's just one less thing I have to think about. So I've got my function f, and I'm going to assume that there is some function eta, which is 3 times differentiable and is 0 on the boundary, and its derivative is not 0 on the boundary. So it's a nice smooth function which hits the boundary, but not in a sort of collapsing way. So I assume I have this function eta, and then I'm going to approximate my function u using this function I call here q, which is eta times s, where s is a neural network, and f is my boundary function. So what does this do? Very simply, on the boundary of my domain, eta is 0, so this term disappears, and I just have q equals f, so I have the correct boundary value. And this means that I somehow have avoided doing anything on the boundary, and I can just focus on what happens in the majority of my space. So I'm going to try and find a neural network, S theta. So S is parameterized by some big, very high dimensional parameter theta. I'm going to find an S such that Q solves my PDE. And by doing it this way, you can see that I've enforced the condition that Q equals F on the boundary of my domain, but the derivative of Q is not constrained in any way. If you just differentiate this, you'll notice that the product rule tells me, well, I end up with eta does not disappear, its derivative does not disappear on the boundary, so this doesn't tell me anything about the derivative of Q on the boundary. Okay, so the first sort of lemma is that if you take your function S in the class of neural networks, which I'll sort of go through exactly what that looks like in a minute, then this eta times S, this is dense in the class of functions which have 2 derivatives and that they vanish correctly on the boundary. I have to write it in some crazy way due to things being almost everywhere correct, but I can approximate any function which is 0 on the boundary and has 2 derivatives by something of the form eta times S. I'm not going to go through the proof. This is not too hard, although it is actually the one point that I really need to have a second order differential operator, or I get H2 here. This is the result that really needs that. Okay. Because I've got the boundary built in, all I have to do now is, if I want to approximate my PDE, I just need to find a theta such that GQ of theta is 0. Now, I haven't said how the neural network is actually configured. It's not really important for a lot of what we say. But the basic idea in what's come to be known as the deep Galerkin method, which was created partly by my colleague Justin Serignano, is you look at you take a large sample of points inside omega, so you sample them according to mu. You take a large sample and then you say, well, let's evaluate how big G of Q is. So I take G of Q, evaluate it at this sample points xi, square them and add them together. And this forms a type of energy over my space. And now I'm going to say that if I have a solution to the PDE, this should have to be 0. But I'm a probability theorist, so I look at this and I go, well, this is a large sample and it's the average. So by the law of large numbers, this is going to be pretty well the same as what I get when I integrate GQ squared with respect to omega, or over omega with respect to mu. And then when I look at this, I get, sorry, there should be a half. There's a half that's appeared here somewhere. And then this turns out to be just the L2 norm of GQ. So this is basically the same as minimizing the L2 error of my approximation. So now I've got my Q and I'm going to try and find a theta so that I minimize this object. Well, what are we going to do? Well, if I tell you minimize this for me, please, you then say, well, that's quite hard to do because Q depends on theta in a nonlinear way. G depends on Q in a nonlinear way. So all of this is very nonlinear. I then square it. So this thing is not linear and it's not convex. It's not quadratic. And I have trouble knowing how I'm going to go about it. But the principle of neural networks is that you don't worry about this for too long. You just say, let's run a gradient minimizer. So I calculate the derivative, approximately try and minimize by taking gradient steps and hope for the best. So what we do is we minimize with the gradient method. So I compute looking at this object or equivalently at this object. I like to think in continuous space. So I'm going to look at this primarily, but of course, numerically, you do this. So you say, well, let's calculate the derivative of this with respect to Q. Well, the derivative of this, well, that's just with the half there. I get, well, by the product rule, I just get GQ, well, it's the chain rule because I've just got a square. Derivative of GQ theta with respect to theta here. And then I take a step of size alpha delta t in that direction. That changes theta into the new value, theta plus delta t. I take lots of steps and hope I can train. There we are. That's the entire algorithm going forward. Well, to analyze this, I'm going to do a few things. I've already done one approximation where I said my very large sample, I can think of it as an integral. I'm also going to take a very small step size, and I'm going to think of this as a continuous training flow. I'm going to think of this as the continuous limit when my steps get very, very small. So I can implement this. It works. It actually really looks like it works as an algorithm, but it's very hard to analyze. The problem is that somehow the derivatives are composed. You're taking the derivative with respect to Q of this differential operator G of Q, and that composition is just messy. In particular, it really entangles the training, the thing that you're trying to optimize, the neural net that I'm trying to use to solve my PDE, and the PDE itself. And that makes it a bit annoying. But there is another way of thinking about this, which comes from optimal control, where you say, well, I'm going to do a crude approximation. So there's an idea in optimal control called Q-learning. Well, what you do is you say, if I'm trying to make decisions, I just make the best decision thinking about what value I will get from my decision tomorrow, ignoring the fact that changing the rule I use to make decisions changes the values that I will have in the future. Okay, so I ignore that second order operation. And Q-learning says, well, let's not worry about this. Let's just go ahead and do it, and proves that nevertheless, these things seem to work. So if I have an approximation of a value function y, so y minus q I'm going to say that's under the Bellman principle. It says, well, what is this? This is approximately the value I get from performing an action over a single step, plus the value I'm going to have tomorrow. What's that value I'm going to have tomorrow? Well, it's just the best value over A of my Q. And notice that I'm not updating at all. I subtract Q from both sides. This is effectively the Bellman equation. And I can call this G tilde Q. Well, what I do if I want to optimize this, if I want to perform Q learning and find this thing, to reduce this error, I just move in the direction where I compute y minus Q times the negative gradient of Q here. And you'll notice, if I put a G tilde here, this looks a lot like the flow I had on the previous slide. So on the previous slide,
what is
yes.
Q, the gamma in that equation, the previous one?
So, okay, so here,
yeah.
Or here?
No, the next one.
Next one?
Yes.
Yep.
Y minus, yeah.
Oh, this gamma is just a discount factor. It's just if I'm trying to solve a control problem, I normally would have a discount factor here. So if I'm solving a control problem, this is what I would look at, and I get something that looks like this. I call this G tilde, and then Q learning says plug it in here and move in this direction. It's a completely ad hoc idea. But the point is, if I compare with this, here I've taken the average over a lot of samples, yes, but I also don't have this G in the middle. The minus sign is still there. So the minus sign sits here, but there's no G tilde sitting here. And so that gives you a different training flow that seems to work. So we're going to consider this as well. Okay, so this suggests an alternative scheme. So instead of differentiating my energy and trying to minimize this, I could actually try and look at this training scheme where I take a step where, so here I've written it in the discrete sense, I move in the direction GQ times the negative gradient of Q, and I might hope that this actually gives me an answer. I don't know. Let's see if it does. Now, when I take my samples to be very, very large, take the limit as time goes to 0, so limiting step, I get a flow, which is the derivative of theta, my parameterization. This derivative is given by minus alpha times the integral of my PDE error times the gradient of Q d mu. And the nice thing is now my terms are decoupled, and this is going to simplify our analysis. So this we call the Q-PDE algorithm, whereas if I go back 2 slides, we call this the deep Galerkin method, DGM flow, and we're going to think about both of these today. Okay, so here is my algorithm, my recipe for solving a PDE. What do? I give you a neural net specified somehow. I initialize the weights of that network somehow. Magic, I just pull them out, I simulate them. They're normally randomly chosen. And then I go through a lot of sequence of training epochs. At each epoch, I simulate a bunch of points using my measure mu. I then I say my approximation is Q theta is eta times S plus F. Here's my approximation. I then either evaluate the deep Galerkin flow or the Q-PDE flow. So I evaluate one of these. I move theta in this direction with some training rate. I then repeat step 2 as many times as I can until I get bored. And I hope that over a long time, Q will somehow converge to the PDE solution. And if I can prove that this happens, then I'm very, very happy, because you'll see that by using neural networks, I'm not ever having to really compute my derivatives using any numerical approximation. And so this can work very well in high dimension. In particular, when I calculate G of Q, this is just going to end up differentiating these one-dimensional objects. So you differentiate, the only nonlinear thing you have to differentiate is a component-wise nonlinearity, and everything else is linear, and linear derivatives are easy to take. Okay, so that's the recipe. So there's a few questions that one would naturally ask. In the limit as the neural network gets bigger, can we show convergence to a nice dynamical system? So if I take the limit as I make my neural net very, very big, can I get any understanding over what Q does? Secondly, if I can understand what Q does, can I show that it actually gives me the right solution? And does it work? And the answers to this are going to be yes. If you take a very, very wide neural network, I can understand exactly what happens when the net gets very wide. It's going to converge to a deterministic, infinite dimensional dynamical system, which I can study. Fairly easy. If I scale the training and the initialization in a good way. Can we show that it converges to the PDE solution? Yes. If the PDE is nice enough, we're going to show full convergence. And does it work numerically? Yes, it does, at least in some test examples. So how do I go about proving convergence of this thing? Well, neural networks, there's various limiting regimes. Neural networks, they're generally made up of lots of different pieces, and you can think of either the very, very wide neural network or the very, very deep neural network. And you can think about different scalings as you make your neural net wider and wider and wider. How do you scale the impact of each new additional neuron? We're going to focus on the easiest case because these things get very, very complicated. So I'm going to focus on the simplest thing possible, where I'm going to get what's called the neural tangent kernel limit. So I'm going to assume that my neural net has one hidden layer. That means that my neural net looks like this. You take an input X, you take a dot product with some weights W, you add some biases B, you apply a nonlinearity sigma, you multiply by some constant C, you add them together, and you rescale it by 1 over n to the beta. Beta is some number between 1/2 and 1. That's going to be the scaling that gives us the limiting behavior we need. And sigma is going to be a function, so it's a one-dimensional function from the reals to the reals, and it's going to have four derivatives, all of which are bounded globally. And it's not constant. That's the only other assumption I need. Can't be a constant. It needs 4 bounded derivatives, and it can't be a constant. Okay. So what's my theta? Well, theta are the parameters. They're the C's, the W's, and the B's. They live in, well, 2 plus D spaces, 1, 2, and D dimensions. And then I've got n of them. So this, you can see, is a flow in a very big space. So my theta parameters live in a very, very big space, particularly n. We're talking here, numerically, we're going to be using n a few hundred. But if you look at large language models, you're talking billions of terms. Okay. So I'm going to assume that I start this thing off. I'm dealing with a flow in theta, so I need to initialize it. I'm going to start them off by randomly choosing my terms. So C, W, and B are all going to be random, initially independently chosen. I'm going to choose C to live in some compact set, like the set containing 0, or the set containing 0 to 1. I could just choose it uniformly. That makes sense. And W and B are both from some distribution which has full support. Say a Gaussian distribution is the natural thing to choose. So I just choose random numbers from in this way, and that's how I choose my C, W, and B. By the law of large numbers, because of my scaling, as n gets very, very large, this object, which I defined on the previous slide, so this thing here, well, when n gets large, these are all independent copies. And so for each value of x, this converges by the law of large numbers to a rather boring limit, which is just deterministic. So it converges to its average behavior completely deterministically. It's very, very boring. In particular, if C is distributed between plus or minus 1, this thing converges to 0. So it converges to 0. The initial term is just very, very trivial. So I'm going to use, I'm going to train theta pretty much as I described earlier. So this Q-PDE flow. Now the Q-PDE flow would be, so I've got this negative gradient of Q term, and then I should have just GQ, but sadly, the world is not always my friend. So I have to clip this thing. And what I do is I apply a clipping function psi, which approximates the identity in particular, but it's bounded by plus or minus 2 n to the delta for some delta, which is between 0 and 1 minus beta over 2. Numerically, you don't need it, but I need it to get enough boundedness to do the proof. So I just clip this thing. Basically, when n is large, this is just GQ, because this term is the identity and this term is 1 when n is large. But I just need this to guarantee that I don't have anything exploding. And what I'm going to do, the final trick, is I scale the learning rate, so the rate at which I train. I scale this by 2 beta minus 1. So my learning rate gets slower as my number of particles gets bigger. Okay. So when I do this, what we do is we get a sort of a lazy training regime, where what happens in the limit is each initial point does not move very far from where it starts. Collectively, all the points move a good distance, but each individual sample doesn't move very far. And this trade-off between what happens in the very large limit, where everything's moving together, so at a large particle level, you do get motion, but at a single particle level, you don't get motion, is one of the interesting things to understand. In particular, what I can get this thing called the neural tangent kernel. So B, which is a kernel over X and Y. I have these eta functions. I have the gradients of my neural nets with respect to thetas. This thing, for a finite sample n, converges to a deterministic kernel for all times theta t. So this is after t time training. This converges uniformly to this deterministic kernel. Now, this kernel is just a function of X and Y. It depends only on properties of the neural network. It does not depend on G at all. You see, there's no G's involved in here. So this is just a property of the neural network that in the limit, this is how it understands the space of inputs. So once I have this kernel, well, I can prove this convergence fairly precisely. I define a norm over the space of kernels, which controls the kernel and its derivatives all having to converge. And I can prove that in mean square, I get these particular rates of convergence between my kernel at time t, at time 0, and with n particles and the limiting case. Everything converges for all finite time. So once I've got this, I can define an integral operator, which is where I just integrate against this kernel. So it's a Hilbert-Schmidt integral operator running on basically the Hilbert space L2, but it's slightly modified because I'm allowed to multiply by eta. So I do that. And this integral operator is very, very nice. So it takes L2 to H2, or actually to H2 with 0 on the boundary. And so it gives me something that lives in the right space. And the main work of the paper is to prove these 4 points. The image of B is dense. So this is my version of the Sebenko-Hornick theorem, that I can approximate anything. So I can approximate any function in this space by evaluating BV for some choice of V. It's strictly positive definite. It's bounded. If I define a norm based on it, the B norm by multiply by B and take an L2 norm, there's a lambda such that BV is bounded by lambda times the L2 norm, or the BV in L2 is bounded by lambda times the B norm. However, B does not have a spectral gap. So the B norm and the L2 norm are not equivalent, which means I do not expect to get any exponential convergence. Such is life. You get these operators. Most operators don't have a spectral gap, and this is no exception. Okay, so what are the limiting dynamics? Once I've got this B, I'm going to be able to give them fairly precisely. I write Qt for my neural network after I've trained to time t. Unsurprisingly, the initial value of the approximation converges to just the boundary value, because the neural net's converging to 0. We can also show that under the Q-learning algorithm, the derivative in time of Q evaluated at a point Y, I can express that just by, well, this is just the chain rule, differentiated in respect to theta times the derivative of theta. look at this for a while and you simplify it down, and you get that the derivative of Q in time is this, where what's this term? Well, F is my approximation of the identity that I was using earlier, and B is this kernel function, which we defined on the previous slide. So now, when I take n to infinity, what happens? Well, everything converges. Qn goes to some flow Q, where Q is an H2, so Sobolev space valued ODE, given by alpha times the kernel B applied to G applied to Q with this initial value. So this is now a completely deterministic object. All the stochastic stuff has disappeared. All the neural nets have disappeared. I just have a flow in a Sobolev space. That's all I need to understand. Okay, and I'll notice that also it always preserves the boundary condition. Look at this thing. You think, oh, that doesn't look too bad. But remember, B doesn't have a spectral gap, so you don't expect this to be a very nice thing to solve. But we can see that the wide single layer neural network, it converges to this dynamical system. I'll just set alpha to 1 because this is just a rescaling of time. So how does this also all relate to the solution of the PDE? Well, we can say a few things. Firstly, if Q converges to a fixed point, then it converges to a solution of the PDE. Why is this? Well, B is a positive operator. So if this is equal to 0, B is a positive operator. So the only way you can get 0 on the left-hand side is for GQ to equal 0, which means I have a solution of the PDE. Done. Well, there are many classical, it's an old problem to study, when does the dynamical system converge? And our challenge here was to try and specify conditions on G and B somehow separately. I didn't want to mix up my neural network and my PDE. Let's try and keep them separate and say what, well, give some conditions under which we have convergence. So one condition on the PDE, which is where you can have Galerkin methods. So if you read old books on PDEs, this comes up. You assume that G is a strongly monotone operator. So if I apply G to V and V tilde in L2, compare this, take the inner product with V minus V tilde, this thing should be sufficiently negative. For a lot of problems, this corresponds to something that has some ellipticity, it's collapsing in some way. So if I assume that this holds, then I can say a lot about my system. But note here, the L2 measures I'm using here, they depend on my choice of measure mu. So I'm allowed to vary this. I can choose my sampling scheme just to make this work. And then suppose G is an L2 mu strongly monotone operator, then I can prove that Q minus U, this, so the average error goes to 0 as time goes to infinity. So in some sense, this goes to Q goes to U. In particular, I can take some set which becomes, after a long time, very, very sparse. So most of the time, this isn't happening. I can take any sequence not in A, then Q will go to U in L2 along this sequence. So I get my desired convergence. The proof, I don't have time to go through. It's basically some weird manipulations and then Grunwald's inequality. It's not rocket science, but it is fiddly. Okay. You can say a little bit more. If I know that I have a strongly monotone and Gateau differentiable map, then I can prove that this integral, sorry, this should not say goes to 0. It should say it remains finite as t goes to infinity. In particular, BGQ goes to U, and that means that either GQ is unbounded in L2 or GQ converges weakly to 0. So I get this convergence not just of the solution to the true solution of the PDE, but of G of Q to 0, at least in a weak sense. Okay, that was enough about Q-PDE. Well, I'll say a few words about the deep Galerkin method, and then we'll see some numerics. Now, it is possible to do a similar analysis for the deep Galerkin method. So this is where you just take the energy differentiate it, and look at this flow. For nonlinear PDEs, it's very, very hard. The problem is that the interaction between the PDE and the neural network becomes intractable. In one step, you can't see what's going on because you're somehow differentiating a derivative. And unless you know a lot about your differential operator, that's not a nice thing to do. For linear PDE, on the other hand, we know from very old results that it doesn't matter what order you take a derivative in. You take cross derivatives in one variable and then in the other, and you get the same result. These commute. So that means that my differentiating in theta and my differentiating in space, they commute as operations, and so I can make my life a little easier. So I'm going to say if I have a linear PDE or more an affine PDE, I'm going to say GU is, let's write it as AU minus little g, and say this equals 0. And I'm going to rewrite everything to have a 0 Dirichlet boundary to make my life easier. And A will be a linear second order operator. Notice I'm not assuming at this point that it is elliptic. I'm not assuming really very much at all about A, just that it's linear and second order. Okay, let's take the law of large numbers again. I go through pretty much the same machinery as I did before. Then I get that the derivative in time of Q, well, Q converges to a new flow Q, whose derivative is U of AQ minus G. Well, what's U? U is, again, an integral operator with a kernel given by this thing. So this is the derivative in C, W, and B of A applied to all of this. And this is the derivative in C, W, and B of just this thing. You look at this and you think, oh, this looks very familiar. I'm very, very happy, except for the fact there's an A here and there is no A here. And that makes me sad because this is not symmetric. And as a non-symmetric kernel operator, it's not so easy to see what's going on. Nevertheless, we push on. If we look at the residual, so I differentiate and subtract G, then I get a dynamical system which has a simpler form. It's just minus SR. What's S? It's again an integral operator, where now I have an A here and I get the same A appearing here. So because I differentiate, basically I differentiate the U that I had in the previous slide. And so I get an A appearing in both places. I look at this for a while and I go, oh, that's nice. That's a symmetric operator. In fact, it's a Hilbert-Schmidt operator. It's positive semi-definite and it's pointwise bounded, but it's only pointwise semi-definite, not pointwise positive definite, and there is still no spectral gap. And this S captures, in some sense, the interaction between A and the neural network, because I've got this differentiation. Now I can change the order of these things, but I've got both of them hanging around in terms of determining this neural network kernel S. And that's different to what we saw in the Q-PDE setting. Okay, so here's the main result that we can prove. If the PDE admits solutions, then any stationary point of my system must be a solution of the PDE. If the PDE does not admit solutions, then there may be stationary points that are not solutions of the PDE. Well, there may be stationary points and they're clearly not solutions of the PDE. But if there are solutions, they can be the only stationary points. Point one. Point two, if I look at this residual in L2, it will be decreasing in time and it will converge to 0 if a solution exists. So if a solution exists, this quantity is going to 0. The convergence is generally sub-exponential, but effectively, if you project to any finite dimensional subspace, you get an exponential convergence on that subspace, at least for non-trivial eigenmodes of S. If I assume further that my PDE operator A has an L2 bounded inverse, now that's true for pretty much every elliptic operator, but also for some others. So if this has an L2 bounded inverse on this space, so as soon as you know you have a solution to this equation, then you know that U has to be bounded by some multiple of G, at least in L2 norm. Then I know that my Q converges to U in L2, where U is the now unique solution to the PDE. So I get the full convergence. The final statement, as I said, it's whenever A is uniformly elliptic and has a discount term, and that comes from Fredholm theory, and you can compare with things like the Hilliard-Sita theorem, if you like. Yes. K is just some positive number. Well, if it's 0, then U has to be 0. Boring. I'm just saying, so if there exists a K such that this implication holds. Okay, so that's, I'm just assuming that some K such that this implication holds exists. Of course, it has to be positive because otherwise the statement is never going to be true. But if there is, so if you have an inverse such that this thing has solutions and they satisfy this sort of a growth bound for some K, then I know I'm going to be able to get convergence. Yeah. And if you have something weaker, it may be possible to adjust the proof, but this is the one that we thought was interesting because it covers all of the elliptic cases. Okay, that's all I'm going to say theory. Let's look at some pictures to finish up. Okay, so we're just going to focus on a simple linear example, but it's a linear example where I can write down the solution. So let's start with a Brownian motion B. It lives in the unit ball in d dimensions, and let tau be the first time it leaves my space omega, and we're going to make omega the unit ball. So I'm computing u, which is the expected discounted time, so the integral from 0 to t of the e to the minus gamma t for some gamma positive, given I start at x. And tau is the first time I leave the ball, so this is how long it takes me to leave the ball. So this equation here, this satisfies this PDE. You can see you get the Laplacian coming in from the behavior of the Brownian motion. You get a discount term coming from the gamma here, and you get a 1 due to the fact that I've got a source term. I accumulate time as I go. So it's 0 on the boundary. And the nice thing about this PDE is it doesn't matter what dimension I'm in, at least if the dimension is even, then I can write down the solution, u, in terms of some Bessel functions of the first kind. And I can compute Bessel functions, so I know how to find this object. So I'm going to use the Adam optimizer. So I'm not going to do quite a gradient flow. I'm going to use a slightly optimized gradient flow because it's a lot faster. I'm going to evaluate the loss as I go through each epoch, and I'm going to choose the point achieving the lowest loss up to some maximum number of steps. I use a varying number of Monte Carlo points. So when I sample my points, I vary the number I sample. I begin with not too many points because it's fast. And then when I get closer to the solution, I increase the number of points. Just increase it linearly because I don't need so many points early on to get a good indication. We tried training it on a GPU. We tried training it on a CPU. The CPU was faster. I don't know why. So what happens? Here's the training loss. So you start your training. You start with something which is not very close to the solution. And this is in one dimension. And the training comes down and it sort of flattens out due to the optimizer. I get this sort of sub-exponential convergence. This is a logistic scale, but it comes down and we sort of get to something, a loss of 10 to the minus 6, that is. And if I look at the actual differential operator, L of Q, or this should be A of Q really, it's of a tiny order, so 3 decimal places. And you can see, so this is the solution of my PDE. And I've drawn here a zoomed in box on a tiny little section. And if you look, there's little dots that are so close to the red line, you cannot see them on the slide. And I cannot see them on the screen because the error is so low. The relative error is of the order of 0.01% for this approximate solution that we get. So I've sort of put some points here. You'll see some points in the coming slides. So this was in one dimension. The problem is boring. It's very quick. It's very easy. I could do this with all sorts of methods. What about in 20 dimensions? So in 20 dimensions, I'm now dealing with a problem which is not easy to write down the solution for, generally speaking. Because it's radially symmetric, I can still plot what goes on. So here's my training loss. So you can see in blue is what happens when you train with DGM. In red is what happens when you train with Q-PDE. And you get this strange phenomenon. It collapses. Then you get this sort of fairly boring collapsing nicely. And then it begins to oscillate wildly. This is a feature of these adaptive gradient methods. You get these oscillations arising. And if I zoom in here, it comes along, it shoots up, and then collapses down slightly lower than where it was before. Goes down for a while, shoots up, and then collapses slightly lower. And if you watch the actual approximation, it sort of does a full move of the entire surface to somewhere and then says, oh, that was bad. If we look at the error, these are the order 10 to the minus 8. The errors in terms of the distance from the origin, that's not so exciting. But if you look here, here is, because everything's radially symmetric, I can plot it. In red is the exact solution. And in blue and red, you can't really see them. If you look very closely, you can see there's some tiny little, this doesn't quite look like a straight line. That's zoomed in just on this little section here. Excuse me. And you can see that it has correctly approximated this PDE. The maximum relative error, so this is searching radially all the way around, the maximum error is order 0.5% at most. And that's very close to the boundary where the function is close to 0, so the relative error is very easy to be big. This was an interesting problem to solve also, because when you start sampling from your space, the vast majority of your points lie very, very close to the boundary because of concentration of measure in high dimension. You know, most points in a 20-dimensional ball lie next to the boundary of the ball. So all your points are living right out here, and yet you get good approximation of the function everywhere, which we thought was interesting. Okay, so to finish up, neural networks, they're quite a useful tool for solving PDEs. There's a couple of algorithms one can use, and they do actually work. Q-learning gives you an alternative to classic stochastic gradient descent compared to the deep Galerkin method. It has some advantages. What you can't see in those plots is about 4 times quicker. You can bake the Dirichlet boundary conditions into the solution, so you don't have to approximate them. And for wide, shallow nets with infinite training data, so in this limiting regime at least, we can prove the convergence of the Q-PDE algorithm for monotone PDEs and deep Galerkin methods for linear invertible PDEs. Lots of things still to do, sort of looking at stability, further experiments, etc. But that's all I'm going to have to say today. So thank you.
Thank you very much, Sam, for a great talk.